I will review very briefly the LTI systems theory concept, that is sufficient to understand what is happening at a later time. But one of the things that I mentioned yesterday and also before is that this representation of a stationary process as a white noise passing through a filter is possible only if the spectral density of the stationary process satisfies certain conditions. And what we mean by the spectral density satisfying certain conditions, the full details we will state later on. But if you recall, in fact I had mentioned this yesterday as well, the spectral density which we denote by gamma, if you recall, is the Fourier transform of the autocovariance function, the discrete time Fourier transform to be more specific, and omega is the angular frequency that we are looking at. This is not the definition of spectral density, please remember that. Many textbooks present the spectral density to be defined as the Fourier transform of the autocovariance function. This is not the definition, but this is the relation named after Wiener and Khinchin that is used in practice for computing spectral density, and we will as I said we will go over this definition much more in detail later on. But the point to note at this stage of discussion is that this spectral density, because we are saying that the stationary process should possess a spectral density that satisfies certain conditions, but for that to happen, first of all, for that process this notion of spectral density should exist, should be valid, and if it is valid only when the autocovariance function is absolutely summable. That we have already stated before, right. We have said first of all the spectral density itself exists only when the autocovariance is absolutely convergent. This straight away tells us that this concept of representing a stationary process as a white noise passing through linear filter is valid only for those stationary processes for which the autocovariance function is absolutely convergent. So, this is an unwritten statement now. Then only we can talk about the conditions that the spectral density should satisfy. There are some additional mild conditions that gamma should satisfy, but the foremost requirement is for the gamma to exist, and that happens only if the ACVF is absolutely convergent. Now, what this means intuitively or is that the autocovariance should have certain characteristics, right, and we know that when a sequence is absolutely convergent it has a certain characteristic. What is that? Any sequence, not necessarily the autocovariance sequence. For any sequence when we say it is absolutely convergent, to give you a hint, at large, in this case at large values of L, right, it decays, right. So, straight away we can say that this notion of white noise passing through a linear filter can be applied to those stationary processes whose autocovariances decay with lag L, right. What does it mean when we say autocovariance decays at large lags? What does it tell us about the correlation structure of the process? Remember, the autocovariance is measuring the correlation between any two observations separated by lag L, and when we require that the autocovariance is absolutely convergent and which means that it should decay at large lags, what are we trying to state with regards to the correlation structure? Well, autoregressive is just one class. When we say decay, it can also mean that the autocovariance has gone to 0 already in finite lags. Those sequences are also absolutely convergent, right. Both the class of sequences that vanish after finite lags and those that decay at large lags, both are admissible. But what does it tell us in general about the correlation structure? It tells us that the correlation, if I take two observations that are spaced long time apart, there should be no memory, there should be no influence of the present on a long time into the future. at least the effect should be diminishing. If not 0, the effect of the present in the future should be diminishing, and that is a very important requirement. Are there stationary processes that do not satisfy this requirement? Are there? Can you think of a stationary process? It is still stationary, but the correlation does not die down at all. We have not discussed such processes, but I mentioned briefly the class of harmonic processes, which are essentially the periodic counterparts, right, the periodic counterparts of the deterministic periodic signals. We said that there are periodic signals in the deterministic world and periodic signals in the stochastic world. The periodicity concept in the deterministic world is fairly well understood. I mean, we are fairly familiar with it, but the periodicity concept in the stochastic world is not so well understood. But I have said this before, that a stochastic signal is said to be periodic if the autocovariance is periodic. That is one of the ways of defining a harmonic process or a periodic stochastic process. Now, when the autocovariance is periodic, naturally it does not meet this requirement, right, obviously, because it exists forever and no way it can be absolutely convergent. But a harmonic process can be stationary. So, which means there are this class of stationary processes, and harmonic processes are quite frequently encountered. It is not a very special pathological situation and so on, it is not that. We do encounter them frequently. So, that means there do exist a class of stationary processes that cannot be brought into this umbrella of white noise passing through a filter. They cannot be brought under this umbrella. So, you have to be clear in your mind when you sit down to fit a time series model. When the moment you say time series model, you are more or less implying that this kind of a model, that is a white noise passing through a filter, unless you state explicitly something else. Yes.
We discussed about assignless noise yesterday.
Correct.
So does that come under harmonic?
First of all, it is not even stationary. So, we do not even discuss that here.
But its autocorrelation is periodic.
No, because the autocorrelation that we are referring to is a theoretical one, and yesterday, as I said, you can't use the theoretical definition of the autocovariance that we have been working with, because for stationary processes. You can apply the definition of ACVF for non-stationary processes. So, by the way, for the audience there who are not able to hear this question was with reference to the signal that we talked about, a periodic signal embedded in noise. Does that fall into this class of processes? But and the answer is no, because straight away you can see the signal is non-stationary. So, this discussion does not even apply. Well, then the question is, if the autocovariance is periodic. Well, the autocovariance that we have been working with is largely for stationary processes. You cannot apply that definition. You have to go back to the non-stationary one and then try to apply, but that is all a bit messy. That is a different discussion. Here we are talking of theoretical ACVS. So, we are now very clear, this idea of representing a stationary process as white noise passing through a filter is applicable only to, of course, stationary processes, but within that a subclass which satisfies this. And fortunately, there are the class of the number of processes that satisfy, or the kind of process, the number of processes that we encounter in practice do more or less meet this requirement. So, it is not an issue, all right. Of course, in practice what we need to ask is, what happens if I know that the spectral density exists, but it does not satisfy those mild conditions and so on. As I said yesterday, in the end whatever model that you build in practice is merely an approximation. You would never know, even if you are given that the spectral density exists, that is the autocovariance satisfies this, you may not know if the spectral density of the process satisfies those mild conditions that we have not stated, or those conditions that we have not stated. So, you just assume that they satisfy and go ahead and build a time series model. What theory says is, if it does not satisfy, then you would be building only an approximation, and that approximation gets better and better as you include more and more observations and more and as you increase the order of the model and so on. But we will talk about that again later on. Right now we are talking about theory. So, let us move on. So, you should keep this in mind that we shall assume henceforth that the process satisfies this condition of absolute convergence of ACVF. Stationarity is always understood. So, now we will talk about an important connection between models and predictors. As you already know, many times I have stated that the time series modeling literature itself has grown out of this interest in forecasting a random process. That has been the primary objective since day one. Therefore, one should expect a strong connection between the model and a predictor, and after all, why am I building a model? For forecasting. So, there should be a connection as well, and we have talked about this. We have said that in fact when we talked about, when we introduced the class of autoregressive models, or in fact particularly when we talked about the role of white noise, we went through this discussion. We said that the goal in prediction is to develop a predictor for this random process, and we said that usually one works with a one step ahead prediction such that the residual has white noise characteristics, right. We assume this V hat is optimal in that sense, that whatever is the difference between the truth and the prediction, that would turn out to be having a white noise kind of characteristics. And from here we developed this notion or this perspective of EK being the input as well, right, not only playing the role of white noise or this ideal residual, but also as an input, if you recall. And we will go through that more in detail now, and we will see that repeatedly white noise appears as an input either in the to the moving average process or the autoregressive process and so on. In fact, that interpretation of white noise being the input that we have also seen in the previous schematic is actually central to the definition of what is called as a linear random process. So, there is an additional restriction now that we are going to bring in. One restriction is stationarity, the other restriction is that the autocovariance should be absolutely convergent. Now, the third restriction is the linearity of this class of subclass of stationary processes. So, again what you see on the screen is what we have already discussed. So, I am going to go past and basically emphasize that now this EK will act as the input to the white noise process. So, to quickly recap the discussion we had, the ideal prediction that one can construct is a conditional expectation. Okay, now, we slowly march towards linearity. The ideal prediction, as we know, is a conditional expectation of Vk given its past. So, given Vk minus 1, Vk minus 2 and so on. Since this is theory, we assume we have the information from the infinite past. So, this is our ideal predictor or optimal predictor. And as we know, to compute this conditional expectation, we need to know the joint PDF. Apart from that, we do know that this conditional expectation is in general a nonlinear function of the past or of the variables on which you are conditioning. If you recall, right, when I am looking at expectation of y given x, we know that this is nothing but some nonlinear function of x, because we are averaging over the outcome space of y. Now, do we want to work with these nonlinear functions? One limitation is I do not know the joint PDF. That itself actually limits the use of this result in practice. The other aspect of this result is that this is a nonlinear function, and typically we do not want to work with nonlinear functions straight away, because estimation becomes difficult, the interpretations become difficult, and implementation becomes difficult, online implementation. There are so many demerits of working with a nonlinear model, at least in the first place. If the process calls for such, no problem, we will consider that. But maybe many processes can be brought under this into this linear framework. Therefore, we want to replace this conditional expectation with a linear model. That is the goal now. So, see that you should see that we are approaching this linear framework only for the sake of convenience, not because we believe that processes are linear. Always, even if you go to the deterministic world, this requirement of linearity is largely motivated by mathematical convenience than anything else, because no realistic process can be thought of as linear. All right. So, there are 2 points when we work with a linear model. The first point is, obviously I am sacrificing some optimality when I approximate this with some linear function. That is the first point, that is I am sacrificing the optimality. But the good news, as we have also seen earlier many times, is that this linear function gives me the same prediction as a conditional expectation if these observations follow a joint Gaussian distribution. As going back to the world of random variables, in general g of x is a nonlinear function of x. However, if y and x are jointly Gaussian distributed, g of x is a linear function of x. So, assuming now that the series or this process has a joint Gaussian distribution, we can straight away postulate a linear predictor and start working with that. That is the idea. What if the process does not fall out of a joint Gaussian, does not follow a joint Gaussian distribution? Then there are 2 things that are going to happen. One, obviously what will happen is your prediction will fall short of the optimal one, but how much it will fall short depends on the extent of deviation from joint Gaussianity, and that is hard to really quantify it. You will have to look at the distribution and then talk about the extent of deviation or violation of joint Gaussianity. What this tells us is, now another requirement, because we are going to work with linear models, it is more or less necessary to test upfront if this whether if the series is falling out of a joint Gaussian distribution. How do we do that? So, look at the restrictions. You know, first we said stationarity. So, this is the big world, right. If you say this is the world of stationarity, then within this we said we will autocovariance should be absolutely convergent. So, which means, you know, we have now a restricted space to work with. What else was the restriction? Sorry, linear or something else? So, one is stationarity, then you have, so let me, maybe some of you are unable to see, I will draw it again here. So, this is the world of stationarity, this big circle, all right. So, let us denote this by S, and then we have, I do not know, then we have this restriction that the autocovariance should be absolutely convergent, then only the spectral density can exist. Further, we said the spectral density should satisfy some conditions. Okay. Then there is a slightly smaller space to work with. Okay. And now further we are saying that I would like to work with linear predictors or linear models, more or less, they are almost one and the same. Now, that means I have a restricted space, and the restricted space is this. So, this innermost circle contains processes that are stationary, whose autocovariance function is absolutely convergent, and the spectral density satisfies certain conditions, and the joint distribution is Gaussian. So, there are this series of restrictions that one has to impose even before we think of fitting this ARMA model. The question of course that arises in our minds is, in practice, does it become too restrictive, right? Are we really restricting ourselves to a very nice cozy set of processes, and that is a comfort zone that we are developing? Well, it is restrictive, there is no doubt about it, but it is not highly restrictive in the sense that it can be, that is this idea of ARMA model, ARMA modeling can be applied to a large class of processes, but there exists a larger class of processes which do not fall within this framework. So, when you are working with a series that has fallen out of a non-Gaussian distribution, then perhaps it is coming from this area, assuming that the remaining 3 are satisfied. So, here is stationarity, here you have the absolute convergence criterion, and then your spectral density satisfying some conditions. So, the spectral density satisfying conditions are denoted by SD here, and then you have the joint Gaussian distribution. So, if your process actually is coming out of this shaded area, or the series is falling out of this shaded process belonging to this shaded area, then and you are still working with a linear model, then yes, you will be making suboptimal predictions. So, how do I check upfront that the series has fallen out of a Gaussian, joint Gaussian distribution? There are tests for joint Gaussianity. One can actually conduct tests for joint Gaussianity. Normally one does not do that, but strictly speaking you should do it. At least visually you should plot the histogram of the data that you have, right. The histogram in some sense gives you an idea of the joint PDF. In R you have the hist command which allows you to plot the histogram in the form of a density function, and you should be at least visually convinced that yes, this data does fall out of a joint Gaussian distribution. It is very hard, it is very hard, because what you are going to work with is a realization. So, it is a very crude thing that you are testing for, but it is much better than not doing anything. It is not a correct representative of the joint Gaussianity. What it tells you is whether these variables are falling out of a Gaussian distribution, that is all. It is not a correct test of joint Gaussianity. If you are truly worried about joint Gaussianity, you should use the tests that are available for joint Gaussianity. Okay. But anyway, most of the series that we will work with will assume that they satisfy joint Gaussianity, but you should keep this at the back of your minds. And if something goes wrong, if your predictions have fallen way short of the reality, then you may want to come back and question this assumption of joint Gaussianity. So, this framework is essentially telling us where to search when things go wrong, when things go wrong, when the predictions go wrong. Ultimately, how do I know if things have gone wrong? I do not know the truth, I do not know the true model. So, the only way I can assess the goodness of my model is through predictions. So, if my predictions have fallen short, then one or more of these assumptions have been violated, right. So, so this is why it is important to discuss the theoretical framework. Anyway, so coming back to the point here, we will work with linear functions assuming joint Gaussianity, and it is with that idea that we went through this example of an autoregressive kind of model. So, one of the possibilities is that the prediction is a linear function of its immediate past only. Of course, the example that we took up the other day was where the predictor was a linear function of past 2 observations. But suppose this is the case, then we have straight away from this equation and this is the optimal one now that we are proposing. We will throw away the star. It is understood that it is sorry, we are always working with optimal predictors, so that I can write this evolution model for Vk. This is only an example, do not think that all processes have this kind of an evolution equation. So, let me actually indicate that clearly. we have then what is known as an autoregressive model of the first order, all right. Now, you can extend this idea to an autoregressive model of pth order. Basically, you assume that a prediction is a linear function of the past p observations, so that you see the model, you get the model that you see on the screen, where you have now a summation of the essentially linear combination of the past p observations. Okay. So, of course, some minor things, we have used a negative sign, and I have said this before. The reason for using this negative sign is so that when I write the transfer function operator, all the coefficients have a positive, they are all represented as additions. That is the only reason.